So to start with, Retrometer is hosting a use case review utilizing OpenEEmeter 4.0 on Thursday, March 14th at 10 a.m. Central Standard Time. They're going to be presenting about some of the work that they've been doing, but we think that this is also a pretty good opportunity for the developers of OpenEEmeter to hear back from the community on how it's being used, what's the user experience with the new API, what kind of features are people wanting, not necessarily like modeling features, but just API engineering features. If you are interested and you are available, you can contact me, Elaine Baker, who is here currently, Matt or Connor, all of that team. All right. Next up, another big announcement that we've got is that we have officially completely released OpenEEmeter 4.0 to the public. You can install it now just using pip install EEmeter. This is on PyPy. As I mentioned last time, the model specification and results are also available. Here are just some snippets at the bottom of the report and of some of the final details. If you're interested in finding this, the easiest way is to Google OpenEEmeter 4.0 and it should pop right up. Another really big announcement that we've got is that we have gotten the Linux Foundation Energy to do a press release for us on the release of OpenEEmeter. A webinar. I should have mentioned the date. I think that is March 12th. Am I correct on that one, Adam?
Yeah, March 12th. So if you've been, especially for those folks who have been involved in the working group so far, it's a great chance to kind of see everything come together. And as nerdy as we are, we've got to keep it to an hour. So you'll get a distillation of the methods themselves, as well as a bunch of work that's been done on the repository. And I would definitely encourage people to come, and I would ask you to share information with your colleagues. We've probably met together as a working group like 15 times, and this is like one of those stopping points where we've got something formal that we want to get the word out. So if folks wouldn't mind, registering and attending, that'd be great. But maybe even more importantly, to share with everyone that you think would be interested in joining and hearing about that as well. So please do. It's on March 12th, and we can send around the link to everybody in the working group to make sure that you've seen it and can pass it on to others as well.
All right. Thank you very much. And then let's just do a quick recap of what we talked about last meeting. And last meeting, we found that where we presented results, that the Elastic Net outperforms XGBoost, AdaBoost, as well as, basically every regression model usable within sklearn. And this is talking about the test error, the computation time, and the model is less overfit than all of these other choices. We found that it has lower error judged by PNR-MSE on cloudy days, and it has lower bias judged by normalized mean bias error. So with that, I am now going to pass it over to Armin to talk about the recent work on the hourly model. Armin, do you want me to click through like last time, or do you want to try it this time?
Let me see if I can share my screen.
Okay.
And I think I did it finally. Here. Okay, can you see my slide?
Looking good.
Okay, great. So let's talk about outline of the presentation today. So we're gonna talk about LSTM model. One of our members here suggested to take a look at LSTM, although we've done it before, but this time we just went in and changed a lot of parameters, like had designed a better architecture to analyze LSTM model to see if actually is beneficial for us to switch to LSTM, use LSTM, or not. And then we move on to calculation time, the comparison between the new model that we have versus the current model, the OpenEEmeter 3.0. And let's see if it's faster, and if yes, how much faster we are. And then we'll switch to something we call a supplemental data. In this case, we wanted to show if we have extra data, for example, EV charging times or pumping schedule, is it going to help us or no? And if yes, how much is better or how much is worse? So let's just start with the LSTM based model. I want to talk briefly about the LSTM module. Don't worry if you don't know anything about it. I'm not going to explain in detail, very high level. That's basically this module tries to forget those unnecessary data at each time step. So we give the module the input data or the training data, and this module tries to forget the unnecessary patterns or any extra data or any noise that we have in the data, and it doesn't pass it to the next time step or the next cell. And this module, this side, is basically responsible for learning new things, learning patterns, or save some necessary or memorize some necessary patterns or data and pass it either to the next time step or to the next cell. That's basically the whole purpose of LSTM, or long short-term memory. So remove the data or save the data and pass it on. That's the whole purpose of it. And this is the main architecture that this time we work with. We work with this architecture in order to train the model and see if we have a good counterfactual for the AMI data. So what's the main architecture? We have LSTM module. LSTM modules inherently very high level, designed to learn the patterns in the time series manifolds. So this module basically gets the input matrix times stacked time series matrix. It can be temperature, GHI, humidity, and all sort of time series that we can have. Pass it to the LSTM module, the blue module, and then summarize it to some vector that is meaningful for us, so we can either pass it to the downstream task, either classification, regression, whatever it is. At this point, we concat that trained vector to the categorical data that we have. It can be day of the week and month of the year, or any sort of categorical data that we have. It can be holiday flag as well. And that's the summarized data that we have. And the fully connected layer at the end is supposed to map that vector to the AMI data, to the meter data that we have, which means the whole thing is summarizing time series and then train classifier or regressor to output our counterfactual or the prediction. So any questions so far? Okay.
Could I just
Yeah.
Can you just like give us a little grounding on the motivation? Like, is this isn't about
Yeah.
lag term, right? This is just sort of general method for tuning, or
This is basically an extra model that we explored a little bit before. So that's neural net, in a little bit more sophisticated neural net. We use MLP. If you remember the other time, the previous presentation, that's basically simple neural net that you can use it with the sklearn library. But this time, based on one of the members' suggestion and our desire to explore a little bit more sophisticated model, we focused on having our own architecture to use this LSTM and neural network in our advantage to see if we can have a good counterfactual or not. So basically, a good deep neural net for the problem that we have. And that LSTM model, by itself, should take care of any lag or anything that we want to. How we do that? With that input matrix. We can have a bigger input matrix in terms of length of time. So let's say we have 3 days of temperature stack on top of GHI and any sort of time series data that we have. And then LSTM module is responsible to learn a meaningful pattern within those time series.
So are we looking for improvements in a particular type of data sets or just across the board?
Across the board, and most specifically on any test error or those k-folds that we had. If you remember, we had the rolling window for 3 years of data. So basically we train it on the in the first year and test it on the next year, and then shift 1 month and do the same thing 12 times. And then we take the average for the test error to compare all of the models that we develop, pretty much all of them. And this is just one other model, and this is based on a neural net and LSTM, just to see, just to check if it's fast enough, if it's accurate enough in the test set. We expect it to be very computationally expensive compared to the auto model, which it's true, and I'll show the results in the next slide. But we expect it to perform better in the tester and trainer. We could see huge improvement in the trainer, because normally deep neural nets can just even push the trainer even to 0, not 0, but like so close to 0. So overfit on the train set, but tested on the test set, it might be not that as great as we think.
Okay, so maybe bringing up the bottom end of the portfolio, better result for the ones that have the most trouble with our existing algorithms.
That could be one of the. Actually, yes, we can see if we have an overkill model. Can we do good in the test set? So if the error improvement is significant, then the current model are lagging at some point in some specific meters, and instead of learning the patterns, we're basically losing those patterns in the current models.
Okay, thanks.
And due to the way that it the neurons connect and whatnot, it also captures nonlinearities that our current model does not.
Yeah.
Okay.
LSTM modules in general, the activation functions at the end of it, it's basically all nonlinear. So that's 100% a nonlinear model. Okay, so let's move on to the next slide. So for each one of these sections that we have many parameters that we can change. We have a huge model. We can change number of LSTM layers or the cells that we have. We can change the hidden size inside of LSTM or fully connected layer, different type of activation functions, batch size, learning rate, and different inputs that we talked about in the time series, and number of epochs, which is really important. So how many times we loop through the training set that we have to learn more meaningful patterns inside of that, and many more parameters that we have. Within these last 2-3 weeks, we changed a lot of these patterns. I don't want to say we reached the optimal model for it, but pretty much a suboptimal model with different parameters that we changed. And this is the result, this is the conclusion of that those 2-3 weeks of analysis. One, as we expected, LSTM model or deep neural nets in general, it's computationally expensive, specifically if you use CPU. And it's 14 minutes per meter. If we wanted to get as good as test error that we have in the ElasticNet. And the reason for that is that first, one, we're using CPU, not GPU. If you're using GPU, this is way lower, 60 times faster, 60. But that in that case, you need to spend more money on the virtual machine that you have. So basically faster, but more expensive and in the computational expense that we have. And not all of the people have access to the GPU. And based on number of epochs, we couldn't see a significant test error improvement. So you can change the number of how many times we loop through the training set to 1,000. But that basically shows improvement in the training set, even though you have normalization factors and all of those things to control the overfitting. But still, we couldn't get a better, very better model with the LSTM. Even though we have a bigger model, nonlinear and everything. That shows a couple of things. That the main reason for that is that we don't have insufficient training data per meter, per training set that we have. All in all, we can have millions of meters, millions of data points, but for each specific meter, for that baseline, we have that baseline. And the way we're setting up the time series, we have 365 samples or the data points inside of each meter or each train set. So that's not enough for a large model to learn. Although if you loop through a different batch size and anything in the trick basically that we have in the deep learning models. And so that showed another point of view for us that maybe the noise of AMI is too much, even within 2 consecutive years, that even with modeling the patterns inside of the baseline, we couldn't repeat that as well as we want with a very low test error in the reporting year or the test site. And that shows even with nonlinear models, we can't do that much. And this is another reason for that is that we having covariates, which is temperature, the weather data, GHI, and anything else. And these are, how can I say it? External variables. We don't have any control. And we want to map that to the AMI data or very high noise usage of each individual meter. So in that case, we don't see the pattern of usage for each individual house consider inside of that training set because we're doing M and V. We're not forecasting. That's it. These two are totally different. So we can regress through the usage itself. We need to use those extra variables. And it showed that maybe this LSTM model is better for the portfolio level modeling rather than individual level modeling. Travis, and I saw a comment.
Yep. So you mentioned no significant test error improvement. What was the test error improvement between
1 and 2% in the population level?
1 or 2% better than the
Better
ElasticNet?
than ElasticNet, yes.
Okay. And you also mentioned insufficient training data points, and that you were doing 365, so instead of doing
Okay.
the 8760, would
So
this
I did both
result?
of it.
Okay.
Yeah, so I
Can you
did
tell more?
both of it. The first one was the 365 because I already had set it up and trained it, analyzed it, and I actually surprisingly with the same thing that we saw in the ElasticNet, if we set it up in a way that we are mapping time series to time series, we get a better result if we have time series and map it to the next time slot and one time slot. That happened to the LSTM model as well. And I thing, and I believe this is based on the noise that we have in the time series. If we do that, we need to consider the hour of the week in the categorical data as well. And that makes the whole model more sensitive to that hour of the day, because the output is noisy enough to change the whole thing. And even if we use L1, L2 normalization or batch norm or anything that we can use in the deep learning, still we get that noisy output. Okay.
Fantastic. Thank you.
Wondering if we have a chart comparing for worst performing. Mustafa, can you elaborate on that? I didn't get the question.
First, I would like to thank you for this extra curriculum here for the LSTM. We anticipate the time of the computation is much significantly higher than the other because of the type of the modeling. But I am more interested to see when you are comparing these two and you are explaining about 1-2%, I would anticipate much more improvement. So I just wanted to make sure we are comparing apple by apple. Like if you have something like a chart showing that the error from the LSTM compared to in both sections, like a training and the test, and then for the ElasticNet or other kind of modeling. I do have other question as well. You may answer that one while you're addressing this one. So would it be possible to separate based on the type of the meters and using, for example, for the meter number 1, modeling approach number 1, which is, for example, ElasticNet, and the other one, LSTM, based on some lesson learned you have from either the location of the meter or type of the building or some other characteristic there. So categorizing the modeling approach based on the type of or attribute of the buildings.
So that would be
can I jump in, Armin?
Go ahead. Yeah, go ahead.
So unfortunately, one of the necessary requirements of OpenEEmeter is that all of these methods are meant to be applied to quite literally millions of buildings at a time. So any site-specific information usually has to be neglected, as that's just not feasible for the purposes of this kind of model. That's more of that's trending towards more of an engineering style model where you can put in things like the square footage of the building, how many inhabitants, and things like that, which those are all very valuable models. They're just not what OpenEEmeter is.
And regarding your first question, training error and test error, because I didn't get any very good improvement in the test set, I didn't bring it. But like if anybody worked with the LSTM models or any deep learning model, if you don't have that regularization factors at the end or whatever tricks that we can use, you can pretty much make the training set error to 0, and you can see the plot is like beautifully follow not just the trend, even all of the noises. If you have sufficient number of epochs and good batch size and everything. But that's not necessarily applied to the test set. And that was the case for many meters that I looked at. And we have to look at in the population level, not individual meter level, because that's not going to be that insightful for us. And that's why I didn't bring it, because the best one had 1% of that 3% improvement that we had. So basically 0 improvement in the test set.
We would also have to look at it at a population level, because if we pick out a certain segment that is doing poorly in one circumstance, that's going to change with whatever alterations to the model that we make. And ultimately, what we have to worry about is not how the model is performing on these set of test data, but how it's performing at a population level, so that we can then infer from that how it will act on meters that we do not know the answer and cannot know the answer. That's the whole purpose.
Okay. Let's go to the next. Okay, so after pretty much setting aside LSTM based on any deep learning model for this pretty simple problem that we have, which is hourly modeling, we will stick to the elastic net from now on. And any calculation or any result that we show is based on the elastic net. If we saw a new model, that basically means elastic net. So for the calculation time, so far I had the data set that Travis provided with that for me from the virtual machine he had. And this time I wanted to see actually with that apple to apple comparison, I wanted to run the current OpenEEmeter in my machine and compare it to the ElasticNet and actually see the computational time and what are the differences. So the test error in the population level, we can see still ElasticNet is better. It's like 3%. Normally in any population at random, you take it for the solar meter is like 3.5, 4% improvement. For the PNR, we see in the test error. And the computational time, you can see here, is almost more than 11 times faster. And I'm happy to say that this is lower bound for this speed improvement. And this is basically for the solar meter. We use all of the data. We have a GHI temperature categorical variable and with the virtual machine that we have. So at least it's 11 times faster. And still the overfitting, we have less overfit compared to the OpenEEmeter. So faster, less error, and less overfit model so far. So all the checks that we wanted to have. Oh, sorry, Adam. I couldn't run it for the OpenEEmeter for the non-solar subsample because it was a little bit, and I couldn't find the data. So next time I will show you.
Lost. It's gone for good.
Yeah.
No, but I think as we're I'll use the opportunity just to color commentate here a little bit. We at this point have gone through a whole bunch of testing of machine learning approaches, AdaBoost, XGBoost. We did the whole decision tree approach. And the elastic net appears to be the best performing. Now we've also done the LSTM and saw only marginal improvement, which I think Travis's point was a very good one, or I think it was Armin's point was a very good one, that we might just be running into the limitations of the noise in AMI data, and the elastic net might already be getting us sort of on the asymptote of what could be expected from a model like this, where we're not necessarily going to have square footage data and all that kind of stuff that he talked about, as inputs to the model. So I've been encouraging the group to start to bring forward more comprehensive results, because we know that this model has to work not only on solar customers, which is a huge driver of what brought us here to work on this problem in the first place, because we know that without solar irradiance data, at the very least, we're not going to do a good job modeling solar PV customers, and that we have that the model is going to be risky applying it to those kinds of customers. But we also need to make sure and demonstrate to everybody that the model is working just as well on non-solar customers, and how we need to approach non-solar customers, and if there are differences in how the model should be formulated for non-solar customers. So I think, the next meeting, just to foreshadow a little bit here, we're going to want to start to kind of set some of the framework for bringing this thing, to a landing. So stay tuned on that. But I think, the fact that we're getting a model here that has better test error, less overfitting, is an order of magnitude faster. And I'll just spoil the, the ending here. It's all this stuff is true also for the non-solar customers. you know, we're the one thing we haven't looked at yet are the commercial customers. So, you know, we're going to want to pull a commercial sample and make sure that everything's looking good there. But I think, you know, we're going to be angling toward finalizing this. So, you know, if you have major concerns or things like that, you know, these next couple meetings are really the time to talk through them. With that, Armin, back to you.
Yeah, just one thing I want to mention for the non-solar meters, and that's actually somewhere between 30 to 40 times faster because we don't use that GHI for that non-solar customers. Okay, next. Okay, so I brought a raw data for one random meter. Here, that's 3 days of data. One day, first day is a cloudy day. The second day is sunny day, and the third day is partially cloudy. And this is raw data. The blue curve is observed data, and the output of OpenEEmeter is the green dotted curve. And any analysis after this is based on this meter and these 3 days. At least the figures are based on these 3 days, and but the training is based on the whole meter data for this specific meter. So as we can see, we're not doing a great job specifically in the sunny day, and this is due to the fact that probably this meter, this household using electricity a lot during the day, even their solar generation is not enough. Maybe there's a party or something, and we can see it doesn't do a good job in a cloudy day because it's not aware of solar data. That's the output of OpenEEmeter. And for the partially cloudy, we're doing all right. And this is the output for the elastic net. So because it's aware of the GHI or solar data, we can see in the cloudy days, which we, in the previous presentation, if you remember, we had the highest error improvement in the cloudy days for the solar meters. And we can see basically in the individual, even daily, hourly level raw data, we can see that that's actually happening. And for the second day, which is sunny day, still that elastic net predicts that we should have solar generation, but that shows how noisy the data is. Even with knowing the GHI, if the household is start using a lot more energy, we can't just predict that. That's pretty much abnormal to the training set. And expand this throughout the whole next year or reporting year. And they're doing basically the same thing for the third day. So I just brought this to see the current model with the GHI temperature and all of the categorical data, how it's doing in an individual level analysis. Yes, Mustafa.
This may be a silly question. If you go back to the previous chart, so by the green dash one, the method of the calculation is that time of the weekend temperature or Caltrack one, regardless of the regression. You use the same kind of library. Is that correct?
That's actually OpenEEmeter, yes.
Okay. So as long as I remember, we have to separate the kind of the data in 2 different zones, which is occupied and non-occupied one, from that time of the weekend temperature. And having said that, if you have additional parameters, like for example, the PV generation, that may impact the occupancy, the separation between the occupied and non-occupied one. Let me give you an example. For example, you have a...
I don't think so. I don't think so. It's just
no
temperature.
Occupancy. The new model, the elastic net, has no relation to the prior OpenEEmeter model. There is no occupancy. It is just the variables being put in.
Okay. So let me comprehend fully what is going on here.
Hmm.
We are looking at 168 different linear regression model here, regardless of the independent parameters. Is that correct?
No, here is just the output of the outputs. Basically, the OpenEEmeter did all of that binning, occupancy, or whatever it does in the calculation that we have, and at the end, this is the output for it. And I just brought,
Let
like,
me
imagine.
let me stop
Hmm.
you there. So
Okay.
my question is, if you consider, for example, one of these time, right?
Hmm.
Let's say, for example, 1 a.m. on Monday. So we have one regression there, one equation, one mathematical equation there,
Yeah.
or 2 a.m. or noon at, for example, Wednesday, we have another regression or another equation. And in
Yeah.
total, for a week, we have 168 kind of equation, different equation.
Yeah.
Okay. So my question is, when you look at the OpenEEmeter, to develop those regression, we are going to separate them in two different zones based on the occupancy,
Okay.
and then use the rest of the kind of approach to develop those regressions. Is that the same when you are doing the elastic net?
No,
Like
not at all. So that's
so,
why
so
elasticity
if
is
if
faster.
this is not the case, this is not
Mhm.
apple by apple comparison. You're looking at
That's
two
model
different
by
kind.
model comparison. So basically, we have some sort of inputs, and whatever we do in the model, it's our choice. That's basically the model. And then the output is the one that we're judging based these two models together. So actually, on the other side, I can say OpenEEmeter use more sophisticated binning and occupied, non-occupied, which I don't agree with that. But Elasticnet is simple. Look at this and predict it. And still we're doing better. So basically we need to have a better model with the input that we have and the output that we generate. So this is the output of those models. You can have that LSTM model. Basically, we don't care about what's going on inside of the model. As long as you give me a good output in the test data set with the lowest error, then you're a good model. Otherwise, you're not.
Okay, maybe I didn't understand the complete picture here. So to me, ElasticNet is a linear regression. The difference is just we are looking at L1 and L2 for the minimization, and you have some sort of parameter to play with. We call them alpha or other hyperparameter there.
Yes.
So to me, the engine is the same from the OpenEEmeter and ElasticNet. The difference is how you define the formula for the regression. As long as you have, for example, all of those parameters embedded or defined in the formula, you should get very similar result. I kind of my question is,
Mhm.
if you do, longest story short, if you do
Mhm.
the same kind of tweaking or treatment in the existing OpenEEmeter,
Mhm.
you should get very similar result to the ElasticNet. Having said that,
Exactly.
I don't.
I'm
Exactly.
thinking.
If I could just chime in here for a second. I think if you go back a slide, Armin, if you don't mind.
Yeah, sure.
So I just want to point out this overfitting score. So one of the key differences in the OpenEEmeter 3.0 versus the ElasticNet is the introduction of a new source of data, which is the GHI. So the models on the next page are not necessarily apples to apples. We're looking at a solar PV customer, so the ElasticNet is allowed to use the GHI. The OpenEEmeter 3.0 does not incorporate the GHI. So there are a different set of variables being passed to both of these models. So they're not exactly apples to apples. Now, you're correct to point out that they're both regression models, sure, but the OpenEEmeter 3.0 is a very structured and rigid, piecewise linear model that has up to 7 distinct temperature bins, each with their own coefficients. And as you point out, and you're correct to point out, there's 2 different versions of that model that are created, one for occupied hours and one for non-occupied hours. Now, the problem with that is there are very few data points when you get down to it. Once you've parsed the model into all of those different sets of data, you have an hour of week separation that is distinct by month of year. And then on top of that, you split that into an occupied set of data and an unoccupied set of data. You have an overstuffed model at that point that you can't really add anything else to if you want to avoid becoming hopelessly overfit. So we're already seeing that even though we're actually providing the model with more data in the form of GHI, we have less overfitting in the elastic net. And trust me, we thought about approaching this entire working group by saying we're going to start with the OpenEEmeter 3.0 hourly model. And we immediately decided not to go that route because we recognized how overstuffed the model already was, given all of those parsings of the data. So that's why we went this route with the elastic net. Now, when you look at the fact that we're getting better results with more than an order of magnitude in increased speed, I think we're on like different footing than the OpenEEmeter 3.0. Do you disagree with that, or what am I missing?
I'm thinking that ElasticNet was part of the OpenEEmeter. If you look at the revision 1.5, for example, okay, that's kind of regression. But here, when we are referring to the ElasticNet, it's just a different, I would say, different problem setup, yes, compared to the OpenEEmeter. Let's say the approach of the time of the week and temperature is not implemented here. And we are looking. So kind of my concern, this is just on the concern that I have. For the existing set of the building, you define a very good kind of formula for that regression, and the result shows a very good kind of fit. If you switch to commercial or other type of the building, the result may be completely different. And you need to tweak those kind of formulation or those kind of engine, like an approach with a different kind of.
For the commercial, we have planned to analyze them in the next meeting. I brought that in the future work in the last slide, but I don't think it's going to be very different from OpenEEmeter. As you mentioned, yes, there are basically linear regression, but the problem setup is different. The inputs are different. The way we look at the data and map them is different. We don't have that occupancy. Maybe that occupancy maybe help us in the commercial. I don't know. I don't think so, but we need to test it and analyze it before compare before say anything about these two models. So that's in that agenda pretty much. Okay, I'll move on to the next slide. Okay, now one of the things that OpenEEmeter in the current setup doesn't have, it's a flexible input. So as Adam mentioned, you have different bins of temperature, you have that occupancy, so everything basically has structure. And you can't just add GHI. Even if I want to add GHI, which part of this process I should add GHI? or any other data that we have. So basically, you need to restructure the time of week and temperature model. So if we wanted to do that, why not just like changing the way we look at the whole problem setup to look at it as just a simple regression? You have the input data and give me the output data. The new model, right now, the way it's set up, we have temperature, GHI, day of the week, month, and usage. The only difference here is the additional GHI and the problem setup. But what if we have new data? For example, pump schedule or the timing of EV charging, just the timing. So imagine for a day, we have a time series of 24, the size of 24, and you have a string of 0 and 1s. 1s show that you're charging your EV, 0 means you're not. And it doesn't show that how much you're charging. So just yes or no. And same thing with the pump schedule. What is the schedule of the pump? Basic 0 and 1. So this is basically the same meter that we saw. That's why I said I'm using the same meter, same 3 days for the comparison. So in this case, again, observed values are in the blue curve, but I just personally add artificial pumping usage, or that can be EV charging. It doesn't matter. Just for the sake of this analysis, I add random electricity usage in random time, but it's basically the mean value is around 8 kilowatt hour, and I add a little bit of noise to it just to make an artificial EV charging type of pattern or pump usage. And these are all random. So I wanted to see if we didn't have that supplemental data or that 0 and 1s, how the model works, which this is how it works, the elastic net without that supplemental data. We just know the temperature, GHI, and all the categorical variables within the data setup that we have. And then I added that extra supplemental data in the time series feature that we have, which is just 0 and 1s, but it's a time series. So basically, ElasticNet doing a better job of predicting those peaks or those scheduled electricity usage. For example, that can be EV charging. And it's around 40% better in terms of test error. And Adam asked me a question here before this presentation. He asked me why we don't predict all of those picks if the sizing is the same. So the way I set it up, it was the worst case scenario. So in the train set, I again randomly select those EV charging times. That's random. It can be in the middle of the day, middle of the night, anywhere in the year. And then I added that extra artificial charging on those time steps. It can be 1 hour, 2 hours, all the way to 4 hours. We can change all of these parameters, but for the sake of this analysis, I just said 1 to 4 hours. We can change the size of it as well. So because we are depending on the time of the day randomly in the train set and day of the week and the month, the model is trying to see if we have inside of that supplemental data, if we have one, somehow take the average of the normal usage and with that extra EV usage. That's why in the test set, because when again we have these times random worst case scenario, we don't see any pattern in the train that we can see in the test set. That's why we have these pretty much halfway picks prediction. If we had the same pattern, like for example, night EV charging on weekends in the train set, and it was consistent enough in the train set, we would have way better EV charging prediction in the test set. So this is worst case scenario. Even in the worst case scenario, we're doing 40% better with the supplemental. Travis.
The other thing that I really want to point out here, so yeah, it's doing a fantastic job with the supplemental data where we're only providing it with on-off, not the amount, but the framework that has been built here allows for the input of any extra supplemental data. That can be daily. That could be, you could throw in a humidity time series if you wanted to, and you can see if that would improve things. This is a very, very flexible input.
And I just want to add on top of that, for sure, we're not going to use all of those humidity and everything. And I don't think we should let the user to choose use all of them. Basically, that's my suggestion, to have set up like temperature or GHF for the solar customers. And if a project, for example, is an EV project and we have that 0 and 1s data, then yes, use it, like allow the user to use it. Otherwise, we will get different outputs based on changing the inputs. So if some other entity can change input and get different outputs, that may conflict with the normal output. Does it make sense, Travis?
Yeah, I was not arguing that we should include these things. I was simply
Mm.
emphasizing the flexibility of the inputs.
Yeah, sure. Ethan, sorry.
No, it's good. So a couple questions here. So one is, and maybe if this isn't something that you intend to expose, we don't have to go too far down into it, but is it necessary to normalize the values of other inputs, or does the model figure out how to treat each one of them separately?
You mean the input variable and output variable?
Well, to normalize the input variable, right? So if you give it a 0 and 1 for charger, and then you've got a humidity that ranges from 40 to 80,
Yeah,
or 0.4 to 0.8.
all of them are normalized inside of the training, and then we transfer. For example, for the output, we normalize the output, we normalize the input, map them, and we have a scaler at the end that predicts and then rescale back to the normal way.
So it's not necessary to come up with your own normalization in order to feed in supplemental time series data.
No,
If
if inside of a config file, if you add it as a training feature, that's the way I set up for the R&D purposes, we may change it in the main file. But if you have in your config, you have that time series in your feature space, that will normalize it itself inside of that process that we have.
Okay. And then the other question I have is, like, some of this starts to look a lot like how some of the other MNV techniques would deal with things like demand response as a flag. So does the model generate some type of coefficient that it associates with the supplemental data time series? Would that be an appropriate use if you were, because I'm thinking, like, so first step down the road is you're like, oh, we've got some participants in a DR program, and so we're going to add a supplemental index that is, was there an event at this hour or not, so that we, sort of disentangle that effect. Like, okay, well, now we fix that. Now the model, like, correctly predicts the expected use during the event. Can you extract the coefficient and say the model predicts that there's a 0.9 kW impact during each event that is directly correlated to the binary flag for the event hours?
I haven't analyzed such a thing like that, and pretty much we haven't focused on DR so far.
Sure.
But the way I think the DR is being set up is that you have a shorter training period. So we're going to have the same model, but we have a shorter period of training set, train it, and then the output. But in terms of the coefficients explaining something about the output or saving, I haven't done any analysis on that, but I don't think that can be helpful. I think the output themselves should provide a better intuition for us. So we have non-participants. Let's see what's the error for the normal meter in the population level, with or without the supplemental data. If that helps in the test error, then maybe we want to use it in the DR event, the participants.
So I think what I heard was there's not a way to extract the coefficients, so we can't directly interrogate the model and ask it how much is it adding or subtracting when the DR flag says there's an event.
So you mean, let's see if we don't have that supplemental data, what's going on in the model, and then add it and then compare these two.
Well, in a typical linear regression, you could just literally look at the table of coefficients and say, there's a slope that has to do with weather, but then there's also an adder for the, that's associated with the event flag. And so like that number directly means the model predicts that if there's an event in any given hour, that will increase or reduce the energy by X number of kW. And so you can literally just interrogate the model and say the model predicts that events shift load by X amount, right? So it's very straightforward. But this is a neural net, so like I understand it's not as simple as that. And I wasn't sure if maybe
you can.
Yeah, I know we can.
So you would just in the prediction, you would simply put the predict what is the output, assume this temperature profile, and assume that this is a flagged DR day. What is the output? And you could then compare that against the same prediction, except you put the DR output as 0. It is interrogating the model, but it is not going into the model guts to interrogate it. It's just it's looking at the outputs, but it's functionally the same thing.
Okay, so but there's potentially interaction effects. So
we can look at two things. So one, we can output the coefficients, and we can look at the coefficients. Specifically, in this case, if we can add the DR into the categorical variable, exactly. It will have the straight coefficients to the output for each hour. So we expect to be 0 for those that it's not in the same hour. And one more thing is that elastic net is not neural net. It's basically linear regression with L1, L2 normalization. So you have the coefficients for it. So you can see the vectors of the coefficients.
Okay. Yeah. Okay. Yeah, I also like the way of interrogating by just adding tripping the flag during the prediction and just see what the model tells you to. But it could get complicated because if there's some kind of interaction effect, it might predict a different effect at different time and weather conditions, which would be interesting.
I don't know exactly how much I would trust that, as that is not really how we're designing this model. It's an interesting application. I'll say that for sure. But I would also say take it with a grain of salt if that's kind of how you're using it.
I mean, it's really not different from the EV charging example, although I have to say that given how that fit is comparing, model to actual in the EV charging, that maybe backs up your caution to not use this as a binary event detector, because it's only predicting like half the impact.
So one thing that I mentioned about this is the model splitting the randomized pattern that we have in the training set. So one thing that I want to change about this analysis in the next future analysis is to add these EV charging with the pattern. For example, at night, and for, let's say, between 2 hours to 6 hours. And that happens, for example, either on Monday or weekend so we have a pretty logical pattern in charging in the training set, we should be able to see the same thing in the test set. So if that's the case, if the pattern of charging is something that we know, then I expect that the model have a way better prediction for these spikes. So that's one thing that I'll definitely take a look at.
Sure. Although this makes more sense for typical EV charging because it's pretty rare that you have such a reliable EV charging schedule. I mean, maybe some people charge for the exact same amount of time at the exact same time every day, but I think
maybe just the
houses.
timing of it. I put it at night. If that's the only pattern that we have, maybe it's just charging at night. If that's the case, yeah, I think still we get better.
Yep. Okay.
Okay, let's go to the next slide. Travis, is there any question in the comments that because I couldn't read them?
I think I've answered them all.
So that was all supplemental data, elastic, LSTM, and everything. So right now, based on one suggestion from Adam, we slightly changed the cloudiness percentage or cloudiness index to make it between 0 and 1 to have a easier way to explain it. So before that, the cloud coverage index was clear sky GHI minus GHI. So basically, if we don't have like how much GHI we're losing for a day. In the new cloudiness percent index, it is in a way that 1 minus the sum of the GHI, all of the solar that we get in a day, and divided by all of the possible GHI we have without the cloud. So this is between 0 and 1. Just change the definition, but the data itself, everything is the same. The model itself, just the point of view. So this is pretty much the same result that we got in the previous presentation. This is for a solar meter population. From left to right in the x-axis, we have sunny days all the way to cloudy days. So 0 means 0% cloud, all sunny days. And as we go to the right side, we have more cloudy days. As expected, and we saw that in before, we have ascending trend when we in terms of error improvement percentage. So basically, this plot shows how much we improve the test error for the new model compared to the OpenEEmeter. So in the more cloudy days, we have more improvement in the test error. So using the GHI for the solar meter is actually working. And this one is the normalized mean bias. This is not percent improvement or anything. That's actually the bias in each cloud beans that we had. So from the left to right, again, we have the sunny days towards cloudy days. As we can see, elastic net is hovering around 0, which means less bias. The ideal model should have 0 bias, but we know ideal is not existing. So this is pretty much the elastic net is doing a better job in terms of bias compared to the current OpenEEmeter. And this is for solar meters. For the non-solar, we have pretty much 1% improvement throughout the whole bins of data. And for the non-solar for the NMB, we pretty much have the same bias for both OpenEEmeter and ElasticNet. Any question about these two figures? This is basically point of view of PNRMSE and NMB.
Wait, sorry, are those the slides that you meant to show with what you were talking about? Because those slides both say solar meters, and they look like they were showing improvement.
Oh, this is just for solar. I was explaining for the non-solar. I should have
Oh, okay, okay.
brought those
No,
figures.
that's fine.
It's fine. Yeah.
I was looking at the charts and it
Yeah,
confused
both
me.
of these are both for solar population. So PNRMSC is doing better as we go to the cloudy days. In general, we have 3.5% improvement, but as we go towards the cloudy days, we have 13% improvement.
Gotcha.
And this is just a bias, a mean bias error in each beans of cloudiness.
Okay, so a couple questions. So one, I think you talked about this before, but the cloudiness is the primary place for improvement because the location from your data set is predominantly sunny, and so the cloudy days are the ones that are sort of aberrant when the model tries to fit everything together without having the benefit of GHI, right? So that's why it's not that cloudiness is inherently complicated. It's the cloudiness is the anomalous day type in this data set. Is that, am I remembering correctly?
Yes, that's basically GHI, but in a way that we can define it in a figure level.
Right, but if this was a data set from Seattle, say, maybe the sunny days would be the ones that had the most trouble predicting because the model had converged around cloudiness because most days are cloudy in Seattle or something like that.
Oh, actually, the data should use those days. I mean, actually, I think the model should do a better job in, sorry, can you hear me?
I think what
Got it.
Ethan was saying is correct. Like, if you were to run OpenEEmeter on a Seattle data set, then the sunny days are going to be the ones that are going to have more error and are going to be anomalous. Assuming that you train them and they are sunny, and then in the reporting period, they're then cloudy.
Okay, so I think still the cloudy day is going to be better because we're talking about comparison between OpenEEmeter and ElasticNet. That is aware of GHI. So it doesn't matter how, actually, I think it's doing better because in Seattle, because I lived in Seattle for a year. So it's like more than half of the year, you have the sunny days. It's not true that it's all cloudy, you know? So there are like 40% of the time is cloudy. So, but the weight of the cloudiness actually can help us to push the whole curve, this PNRMC improvement higher actually, because more of these data sets on the left that have less improvement will move to the right side and bring the whole thing up. So instead of 3.5% in the population level improvement, I would expect 7%.
Okay. I mean, it's not like there's a trade-off between some days we're seeing one model do better and other types of days we're seeing the other model do better. The new models are beating them on all the days. It's just beating them by more on some of the other days. So it's kind of an academic question. My other question was about the distinction that we keep making between solar meters and non-solar meters, and some comments that you had earlier about how only for the solar meters do you allow GHI to be used.
Mm-hmm.
And so I'm assuming that in most of these examples, you are passing in the is meter solar flag as one of the categoricals that then the
no. So the way the way I do it, we have set up for non-solar customers and solar meters. Sorry, non-solar meters and solar meters. And I have the same model for both of them, but the inputs can be different. We saw that if we just use temperature in non-solar meters, we're doing slightly 1% better compared to the time that we use temperature and GHI. As Travis mentioned before, we might just use temperature and GHI for all of them because because it doesn't make sense. Like that difference is so tiny that we might not care for the non-solar.
Well, and part of where my question was going was, I mean, a lot of times in utility data, you do have a relatively reliable flag for solar customers because there are typically some policies that push people to self-declare before they connect their solar. So you might have a pretty good idea, but I was just trying to figure out whether this expected that we would be able to distinguish solar and non-solar and set up the metering code differently for solar and non-solar. What I'm hearing you say is that that's probably not necessary, and that it would be a reasonable thing to just use the new code with GHI, throw everyone in there, whether we think they have solar or we don't think they have solar. Don't worry about whether we know the answer, and it will use GHI for what helps and not for what doesn't, and don't worry about it.
Yes, that's true. And on top of that, actually, even if we have that data, that solar, non-solar, true, we can actually change that to 0 and 1 and append it to the categorical data.
Sure.
That's another idea that we can explore too.
Yep.
So let's move on to the future work, which I think I should add another one. Because we had a conversation here. I don't remember exactly which one was it. So the first one we wanted to do is put this new model, the structure, like pretty much migrate from R&D to the API format that we have in OpenEEmeter, change the code, more engineering rather than R&D from now on. Bad news for me. And adding NMBE into the loss function for the elasticness. So here, real quick here, the NMBE, it's a little bit up and down for the elasticness. It's better than the current model, but still we might be able to improve that without hurting the PNRMSE. And the way we do that, we have a custom elasticness rather than just use, which is a subclass of sklearn. I changed it before this presentation. We can change the loss function and add the bias into that and optimize on top of that. So that's something that we need to explore to see if that actually help us a little or not. And commercial samples, as Mustafa mentioned, that's one of the parts that we definitely we need to explore to see how the model is doing over there. And the hyperparameter tuning for a huge population level. So instead of, right now we have fairly a good idea of what are the main hyperparameters should be, but to optimize it, we need to go dig a little bit deeper on that. Sorry, question. What if solar wasn't in the household and then had a certain point? That's one of the things that we need to actually use the solar disaggregation, I think, or solar customer detection. That's one other, that should be another project, because you need to actually roll through it. I thought about this problem. This is totally a separate problem from hourly model. That should be a solar detection. So which you need to have a rolling window to actually flag a solar installation. That's going to be another project. That's actually true, Ethan. If we have that extra data that from now on you have ones, which means you have solar, then yes, use the GHI. That totally makes sense.
I just worry, like, how accurate is that going to be? Because that is going to be a lot of days where the building might be, the underlying building, not just including the additional solar panels, might be behaving differently compared to how the building acts once they are installed. And if you're trying to put all of this in the baseline period, then that is going to be a reduced amount of data for either one of these categories.
Yeah.
Well, but
yeah, you're right.
I didn't think what we were talking about was like zero out the GHI data during the days when solar wasn't installed. It's provide the GHI data for the entire time and then provide another set of time series data in the independent variables that is a 0 for the pre-install and a 1 for the post-install. And then in theory, the model would interpret GHI plus that 0, 1 in two different ways, right? That the one would tell it, oh, now boost it.
But we're gonna have one problem here. So it depends where that solar installation happens. If it's in the baseline, if it's in the middle, the model should split between these two. That's the only way the model can interpret because of the loss function. If we have more data towards like end of the year, so that impact is less. If it's in the beginning of the training set, so the impact of GHI is higher and it's better because that more represent the reporting year. So it depends on where the installation can happen.
Yeah, it actually sort of begs the question of revisiting the data sufficiency criteria. For the existing hourly model, the data sufficiency criteria seem to be very focused on, or like very dependent on the formulation of the model itself. And the model itself there's an independent model that is generated for every month that depends on that month plus the neighboring months on either side. And so only 3 months of data are being utilized to formulate the model at any given point in time. So because of that structure of the model, the data sufficiency criterion is very restrictive in a way. It says you have to have 90% of all data for every single month. And anybody who's worked with hourly data knows that you're going to eliminate a lot of meters based on that criterion. But with the reformulation of the model, potentially we can go back and we can relax those data sufficiency criteria, significantly. And if so, then maybe it's possible we can build a model on 6 months of data or 8 months of data or whatever it might be. And then if somebody gets solar PV installed, like relatively early in the baseline period, potentially we can just ignore that chunk of data. I do think it's difficult if in the reporting period you have solar PV installed and you have relatively little data in the baseline period to build a model to represent that case. The model has to understand what the building's response to solar PV, to GHI, solar irradiance is. And I would argue there's clearly a seasonality associated with that. So you want to capture that, I would imagine. So it's definitely something that I think we have an opportunity to maybe at least relax some of those criteria. I'm a little bit skeptical that it would be wise to try to like really parse things out in this kind of way, because ultimately I would imagine the goal has to be creating a model that you have confidence can represent the state of the building, in a counterfactual sense during the reporting period.
So those cautions make a lot of sense, Adam. The new Elastic Net model, is that also building a separate model for each month, the way the old OpenEEmeter was?
No, just one model. And we consider that month of the year as one of those categorical variables, which when I say one, it's actually 12. So it's a vector of 12, and whatever month you are in, that entry is 1, and the rest of the vector is 0.
Okay, so it could have some influence, but it might have less influence. It's not like if you're missing a month that you can say nothing. Well, but then so what would the model do if you were missing one? Because I was about to ask, with all this stuff, like if we need to go back and revisit some of the data completeness requirements, which Adam, I know you were saying no, we shouldn't, but
well, that is a good question. I mean, I actually don't know the answer to that. I mean, do you have what happens, let's say, if we're just missing all of January in the baseline period? What happens with the counterfactual?
So basically, we are training on that 11-month, and we shouldn't have a good model for January because we haven't seen that. But still, based on the trend of the other months, we should be able to have a fairly good counterfactual, given the fact that we haven't seen that data in the previous baseline.
That 1 through 12 is a categorical, right? It's not interpreting it as a scalar, right?
No, it's not a scalar. It's propagate itself to all of the output. But if it's random, the impact should be 0. That because we are not optimizing on that specific one entry. We are doing actually, if it's, for example, let's say January, the first one should be 1, the rest of it should be 0. We don't have that. But for the rest of the data, when it's 0,
Armin?
go ahead.
I'm not sure that this is right, because if every other month it's going to have some variable associated with the month, and if you now are trying to predict on a month which has no monthly component, then you are going to be missing plus or minus something.
Well, that's a question. It's like, is it a little bit wrong because it's just going to like fall back to some kind of average across all the months? I mean, the other way, like thought experiment, like give it a month of 13. What do you think? Here's some weather from month 13. You've never heard of month 13. Does it just roll with that and be like, well, it's an average month, you know, or does it freak
start
out?
modeling like Neptune? You know, there's a lot of months.
I think actually it's not doing as bad as we think, because it, like that model saw the relationship between the temperature and GHI with the output. I know those categorical variable helps, but those time series have a bigger coefficients that connects to the output. So it's a matrix of coefficients. Those time series features have a very strong relationship with the output. So if we have the temperature and GHI for that month, I think we're gonna be able to have fairly good prediction if we don't have 1 month.
Well, let me ask the question in a broader way, because we're almost out of time, and
Yeah.
I mean, probably if we really wanted to answer the question of can we do without January, you know, you could 5 minutes of running a test set would answer this question better than our thought experiments. But generally speaking, right, like in the prior version, we did have this very strict, like we need 12 months. And we also did some experiments with the, you know, daily and the hourly models and said more than 12 months is hurting more than it's helping, because you're more likely to get, you know, different behavior from the further back in time than you are to improve it with a larger data set. So we like went through a whole empirical process to come up with the answer of like exactly 12 months is the right answer, and we should be pretty narrow about that. And I just maybe want to generally ask the question, like maybe now that we have this more dynamic process where we're actually like using all the variables sort of overlaid on each other instead of like explicitly creating these submodels, could that maybe relax the data requirements? Like what if we were missing 20% of data scattered throughout the year, right? So like the totally missing January problem is a pretty nasty one. You know, it's kind of hard to like build a model on that kind of, you know, baseline. You know, we have said before that if you've got like one shoulder season plus heating and cooling, maybe 9 months of data is enough. That might be worth experimenting on. But just like generally speaking, should we sort of revisit this question of like doing some degradation on some of these data sets and seeing if the new model is more resilient to data loss, and we should recalibrate our standard for minimum data requirements?
I absolutely think the answer to that is yes, both for the hourly model and the daily model. Basically, all of those requirements, I think at some point we need to revisit them. I don't think that now is a particularly good time to do that, I think that we need to finish the model, wrap that up, and then we can basically start a new process of evaluating whether we want to change our requirements. So for now, I think we stick with the existing conservative requirements because we know that they're at least going to work with what they are.
Sure. Yep. Okay. Thanks.
So in the last minute, I wanted to just bring this up so that we can think about it in the next, I guess, 3 weeks. But there are some really, so with us opening up this supplemental data, there are a lot of interesting things that can be done. I'm also worried about those same things if we are trying to say that the base CalTrack, or not CalTrack, a base OpenEEmeter will provide you with quality results. Do we need to limit what can be put into that supplemental material or data sets? I think the answer is probably yes. But I think that this still provides an interesting opportunity for people to play with the model however they like. They just have to say that it's not compliant with the existing OpenEEmeter standards.
Yeah, along those lines, if I could make a suggestion, and certainly I think this is worthy of a longer discussion with other folks, particularly maybe after we've had a chance to play around and see, just how dangerous we are with the new tools. But so there's another project I'm working on, and one of the things that we've done, because we've allowed a lot of variation on the inputs, is to have a structured output or like a parameters file that says like this analysis was done with all of these particular coefficients going into it. Like these were the variable choices that we made, so that when you're looking at all the different data sets you have coming out, you can be like, oh, I want this one. Like that was an experiment that I decided I didn't like, so I don't get confused with the output data, right? So we basically make a JSON file that says, here were all the different choices that went into this huge set of data outputs that happened later on. And so maybe there is a way of creating this kind of like, configuration artifact that says, here's what went into it, so that you can then say, well, is this CalTrack standard? And I think, to your point, Travis, like this is something we've done in the past, which is you can pass some, some weird parameters. Like I've done some OpenEEmeter runs where I'm like, I'll take an R squared. Anything better than 0.2 is good enough for this purpose. Like, we're not paying on it, but like we want to look at them all, so we won't throw them out. We're going to be very liberal with them. So being able to distinguish between a sort of program CalTrack standard and just like what you're allowed to play around with if you want to do a science project, it was a really powerful feature in OpenEEmeter. And so I would certainly advocate for, yes, let's have a shared standard that says this is what we think is best practice, but also playground.
Fantastic. Okay, we are already 2 minutes over. I really hate to cut it off because this is a fantastic conversation on multiple threads, but I hope that we can pick this back up at the next meeting. Thank you, Armin. Thank you, Mustafa. Thank you, Ethan, and everybody for your great questions. And it's just been a fantastic meeting.
Thanks all.
Thanks for all your work, guys.